Okay, hi. Let me finish the Stokes theorem. So we have some more examples that we need that I need to share with you, so that you will become more clear about the Stokes theorem. Okay. As in the example in the notes, there is one question where it is example 5.22. Okay, so the question here, evaluate the line integral where the f is given. So we have a vector function, and the c here is the circle with radius 1, and then z equal to 0, and oriented positively. Okay, so the question here, maybe this one is just understanding on how we use the Stokes theorem. Okay, so the question here, why the Stokes theorem cannot be applied in this case, meaning that the idea here is, we know that in the Stokes theorem, so if you are given they ask you to evaluate the line integral given by f dot dr over the curve C, where in this case your curve is, it looks like a closed curve, right? Because we have a circle given by x squared plus y squared equal to 1, and then it is located at z equal to 0. So we have so if we sketch this, so it looks like we have a curve in space where the circle is lying on the floor. Okay, so if you sketch it, so now on the floor where z equal to 0, you have a circle with radius 1. Okay, so this one is curved, so you have a closed curve here. So then the question here, you have to explain why the Stokes theorem cannot be applied. So the idea here, if we understand what is the Stokes about, so the Stokes says that the closed curve that we have becomes the boundary of the open surface, where the value of given by this one, this line integral, is the same as the surface integral of the curve f dot n yes, over the surface sigma. So this is the Stokes says, which means that if they ask you about this, so in this case, if you try to use the Stokes theorem where you compute on the right side, and the answer will not be the same. So here, why it cannot be the same? Okay, so the question here is, or the question here, why the Stokes theorem is not applicable here, where it is give you the different value from the left on and also on the right side. They are a different value. That is because of, okay, now you look at the condition to apply the Stokes theorem. At the beginning of the Stokes theorem, where is it? Let me, where is the Stokes theorem? Oops, sorry. Okay. Where is the, okay. So this, okay, so if we look at here, Stokes theorem, we assume that C be any closed curve will be the boundary of the surface sigma, open surface sigma, and F here is a vector field that is continuously, so the keyword here says that continuously differentiable. Okay, So F is a vector field, is continuously differentiable on the surface. Okay, on the surface. So now we look at the F. In this case, we look at the F, the vector field function, this one. So the vector field here is negative. So now our F is given by negative y over x squared plus y squared and x over x squared plus y squared. Okay, so the conditions say that the F should be always continuously differentiable, which means that always can be differentiated over the surface sigma. So the surface here is the z equal to 0. Okay, z equal to 0. So any point on the floor, okay, z equal to 0 and bounded by the x squared plus y squared equal to 1. Okay, so meaning that, so this is your surface. So this is your surface. So you have a surface where the boundary is given by the closed curve of x squared plus y squared equal to 1. So that is your surface sigma. Okay, so now look at your function here, this one. So if you look at the value, okay, now the problem is how can you say that differentiable, meaning that can be defined at any x and y on the surface. So if you look at the denominator here, so is there any condition? So just focus here. Is there any condition so that you can see that F is always can be defined at any x and y on the surface given here, this one. Okay, so you will see that the component x and the component y, the vector function here, can be defined. There is a value exists for any value of x and y except where? Except at the point of x squared plus y squared equal to 0. Why? Because if we put minus y over 0 and also x over 0, so the answer is does not exist. Does not exist. Okay, because this one turned out to be the value which is undefined. This is not real value. So or we can see that the component x and the component y here exists all over the surface except at the x squared plus y squared equal to, or at the origin. Okay, so meaning that the function here the vector function here is can be defined at any x and y on the surface. So the condition for the Stokes theorem is not fulfilled. Okay, so that you cannot use the Stokes theorem because of this condition is not met by the vector function given. So the vector function given is not continuously differentiable on the surface sigma because of the value here does not exist when it is exactly at the origin, where origin is part of the surface. So that's why you cannot use the Stokes theorem for this one, where when you compute the left side and you compute the right side, the answer will not be the same. Okay, so but in exam, normally the for the sake of exam, so if you look at the past year question, final exam question, they always asking you to compute the whether this one or this one using Stokes theorem. So meaning that since they ask you to do so, then meaning that the condition to apply the Stokes theorem is met. Okay, so we don't bother about that. It's just about the understanding why sometimes the Stokes doesn't work because of the condition is not fulfilled. Okay, So and then how can we solve this one? Okay, back to the question here. So how can we solve this since the Stokes cannot be applied? Meaning that you have to compute manually. You have to use the straight forward method where you just need to compute the line integral as usual. Okay, and you know here your curve here is closed curve. Okay, so since now your remember the Green's theorem. So what is the condition to apply the Green's theorem? So you can apply the Green's theorem if your curve is closed. So now it looks like we have a closed curve, and then we have a 2D system where ing. So actually this one is Green's theorem, where yes, we know that the Green's theorem is the one of the as I mentioned before, Green's theorem and Stokes theorem actually they are related to each other. The Stokes can be we call it as Stokes because we have the closed curve in space, like this closed curve in space. But for Green's theorem, so we have a closed curve on 2D because now z is equal to 0. So you just only have 2D where just y and x, and it is closed curve. Okay, so you have a closed curve. And there is the word oriented positively. So oriented positively, as I mentioned before, oriented positively for Green's theorem, so it is always anti-clockwise direction. Okay, so that is the meaning of oriented positively. Okay, which is it is you can see that oriented positively means for Green's theorem it should be anti-clockwise direction. Okay, so in this case, whether Stokes or Green's, both of them are not applicable because of the function f. So the reason here we can see that y, so the answer here, so why they cannot be applied? Because of the function f cannot be defined at the origin, where x squared plus y squared equal to 0, right? F cannot be defined at the origin, where we know that origin is part of the surface sigma as given in this case. Okay, alright, so since Stokes and Green's cannot be applied, and of course you cannot apply the Gauss because you don't have a solid here, so we have to compute manually directly using a line integral. Okay, so in this case, if you sketch the that is your curve, right? That is your curve. Okay, you have a circle with radius 1, so that is your curve. So since you have to compute it looks like you have to apply the line integral where f is given here, and you have to obtain the r. Okay, so over the curve, so your curve is a circle. Since it is a circle, so as we know that, okay, you have a circle with radius 1, so x is 1 r cos, I'm using t, and y is r sine t. So that is the simplest form of the parametric equation for a circle with radius 1. Okay, where r actually there we have r cos theta. So in this case I'm using t, so r cos t, so r is 1 here, right? So that is why we have 1 cos t. So this one is supposed to be 1 sine t. Okay, so the x will give you minus sine t, and dy will give you cos t. And then so f dot dr, so then your f, okay, so you have to convert your f in terms of t. So minus okay, so I put the f, and the r, we know that the r, there is a dx and there is a dy. So the x here is minus sine t, and dy is cos t dt. Okay, so then this one also need to be changed to t. So y is, as we know, sine t, there is negative here. X squared plus y squared, you have to use this one, so we got 1. Okay, and this one negative sine t, and this one also x is cos t, x squared plus y squared is 1. So then when we simplify, we have sine squared t plus cos squared t. So this one is equal to 1 from the identity of trigo. So then we can integrate the t, so dt, so we got t, and the answer is 2 pi. Okay, so this is the result, okay, of the line integral if the c is a closed curve like this, where without using, here we compute without using Green's or Stokes theorem, because if you use the Stokes or Green's theorem, the answer will be different. Okay, so what is the answer if you use that? So the answer will be 0, where the answer is not the same as when you calculate directly without using any theorem. How can we know the answer is 0? So imagine now we apply the Stokes or Green's theorem. So I say we can use Green's here because we have 2D, okay, or this one. So from this, when z equal to 0, so it transforms into 2D where we have this particular shape. Okay, so what is the formula to apply the Green's theorem? So to apply the Green's theorem of the closed curve f dot dr over the closed curve c is given by the qx minus py dA. So this one is a Green's, which is as we know the extension of the Green's we have Stokes. Okay, but Green's only 2D, Stokes for 3D over the region R. So what is Q? What is P? So this is your P and this is your Q. So when you differentiate Q respect to X, so then try to differentiate partially. So this is your Q, we differentiate respect to X, so it looks like we have to apply the quotient rule. So V x squared plus y squared v du dx will give you 1 minus u dv dx, you got 2x over x squared plus y squared square. And when you simplify, you will get x squared minus 2x squared. So you get minus x squared plus y squared over x squared plus y squared square. And then p, okay, what is your p? P is minus y over x squared plus y squared. So py, so we apply the same quotient rule. So v du dy, so we got minus 1 minus u v du differentiate respect to y divided by v squared x squared plus y squared square, and you will get minus x squared minus y squared minus 2 y squared x squared plus y squared squared. So Okay, I realize this one's supposed to be positive. So we will get minus x squared plus y squared over x squared plus y squared squared. So if you have a qx minus py, so look at your result here. This one and this one, they are the same, right? And the answer is 0. So if you substitute qx minus py, where the integrand is 0 dA, and the answer is 0. But is that correct? Now you compare with your calculation just now, using a direct method, you got 2 pi. And that is why the answer is not the same, because actually the Stokes and the Greens are not applicable here due to the condition of them for the given f is not fulfilled. Okay, where f cannot be defined at the origin, where the origin is lying inside the surface of z equal to 0, bounded by the x squared plus y squared equal to 1. Okay, so hopefully you understand that. So I would say that not always, not all the time, the Stokes and the Green can be applicable. It depends on the vector function provided. Okay, so that is another example, another thing that you have to think about, where it's not all the time Stokes and Greens are applicable. Okay,